fine. $250. We don't need to spend much more to get the room.
Did you see how I worked on the rudimentary prototype?
Yeah. All right, is it recording? Okay, we're Team1, the intelligent stethoscope. Our advisor is Jim Weimer. This is Jonathan. I'm Matt. Jason. This is Jared. We usually communicate over Slack, over Messenger. We tried WeChat, but we're not too good anymore. Okay, so a smart or intelligent stethoscope. What is the problem we're trying to address? One, there's many use cases for this product. The major one that we're looking at is heart murmurs. There are children who die of undiagnosed heart murmurs. The problem is that only highly trained cardiologists actually know what a murmur sounds like. So you've probably gotten, like somebody put a stethoscope to you and listen to the signal. But to actually say whether there's an issue with that signal takes years and years of practice. And so the idea is there's not a cardiologist everywhere to validate that for you. So we know something about signals processing. Why can't we try to detect whether there's some issue, or at least make a recommendation? You should go see a trained cardiologist. And the validation of this idea is that Dr. Brooks is really excited about this. He was the advisor for one of the previous projects Sid was talking about. Yeah, so the goal is to create the stethoscope that listens to the specific frequency and pattern associated with murmurs and crackling in the lungs and other health issues. And the near-term goal, and John will get a little bit more into this later on, the near-term goal is just specifically for heart murmurs, and the longer-term goal is to add in other biometrics to see other potential issues that we can diagnose. And the overall idea, what Jim Weimer calls it, is the check engine light for the body. And if it's something you can constantly be wearing, then it can get these signals and tell you proactively you might have some issue.
Even just giving you access to that constant monitoring of data is really important. And that's another use case for this device. It's just looking at that data.
So do you want to talk about the existing product?
Sure. So there's currently very few, surprisingly, existing products that match exactly what we're looking for. So what you see right here, this beautiful picture on the right, is the Echo stethoscope. That doesn't at all do what we want. It's just a nice picture. But what this does do is that it amplifies specific frequencies that does make it more useful for doctors or nurses to listen in to specific spectrums that they already know that they're looking for. What doesn't exist so far is the ability to have a solution where you just place it in the general area. It tells you whether or not you've placed it actually in the correct spot. And surprisingly, that is a problem that many nurses come into. And then it also then analyzes whether or not you should actually go see a nurse or go see a doctor. So what we're thinking right now is these existing prosthetics that are already out there on the market don't exactly fulfill what we're looking for, which is something that tells you whether or not you should be going to see a nurse. So our milestones are quite succinct for this first semester. The first thing that we want to do is create an all-in-one package. We're looking specifically at doing a custom spin-up of a PCB if Sid finds the money for us. He's shaking his head. But we are looking to do our own PCB. Specifically, we chose the STM32 microcontroller platform. We've got extensive experience for that. It's also very expensive, Sid. So we're hoping that we were able to use that. We're also looking to do all of our embedded development in C. And our minimum viable product, at least for the coming milestone, is to create a breadboard version of this or perf board version of this, just to validate proof of concept. We also want to start in parallel, specifically Jared and Jason will be checking out our database of heart murmurs, which we've already identified online. This is a database online that tells you a supervised model of whether or not this sound has a specific heart murmur. So these are two parallel things that are happening. The first side is a machine learning classification problem that might end up actually just being signal processing. And then the other problem is figuring out whether or not we can build a device that does this. Once we have these two things together, then we move on into the spring semester where we integrate the two. One of the key challenges that we've identified really early on is whether or not the online database of heart murmur sounds or the online database of heartbeats in general will actually match the sound signature that we pick up using the stethoscope itself. This is actually a really nuanced and subtle problem because what we'll have to do eventually is normalize the sound our stethoscope picks up. That is to say, over time match it such that its base signal does match the base signal of the online database, and that's the only way we can accurately create a fused network in which we use the online database to tell the user whether or not he or she has a heart murmur. We also have a lot of different additional features that we did want to explore. Some of these are rather simple, like adding thermistors to tell constant temperature the skin. You can add a pulse oximeter, which is quite simple to build. One of the key things that Jim Weimer was very excited about was adding a haptic engine so that you would actually be able to send a pulse, a vibrating pulse, down towards your ribs. And it turns out that specific sound signature will be returned if you place it directly in between your ribs. And that's actually where you want your stethoscope to be. And this is another problem that many EMTs and many cardiologists have identified as being a problem out there. The technologies we use, as we mentioned, are digital MEMS. We're choosing between digital MEMS microphones and a piezoelectric microphone. There are different merits to using either one. Our hardware for now, we're going to start out with the Arduino Zero medical tape, and that's going to be something that we medically tape or patch down to your chest. And then lastly, for software, we're preliminarily going to be using TensorFlow unless we find that fast Fourier transforms become a much better option, which is something that we'll look into as well.
And hopefully as our product gets used more, just because there's more and more data out there, and if it becomes widely used, hopefully it can improve the existing data that's already out there. So continuously providing the user with the indicator that they need about the patient, and also improving the system for it to be used in the future.
Yeah, and that is our idea. Thanks.
Thank you.